Hello everyone, welcome back to CSC Core Concepts in the series of machine learning algorithms with implementation in RStudio. In this video, I am going to demonstrate about your principal component analysis, which I have discussed in my earlier videos about what is the working of principal component analysis and basically what is it used for. So it is a feature extraction technique. So it reduces the multi-collinearity problem, that is those features which are collinear. So that will eradicate and it is going to derive new feature from those features. So the data set which I am going to use for demonstration is the iris data set, where there are 4 features which describes the type species of iris is a flower. So there are 3 species: iris setosa, iris versicolor and iris virginica. So this variation in the type of species depends on the 4 parameters, that is the sepal length, sepal width, petal length and petal width. Okay, so basically it is a classification problem. So let us first of all include the library file. So out of these 4 features, what we are going to see is that which features are collinear, okay, or which features can be derived, right? So the library file which I am going to use is the psych library file. So let's say iris data, let us read that CSV file. So see, you can also this RStudio does have iris installed, so you can directly get the data set from there, or you can just have your package and you can read the data. So it is a data frame having 150 observations of 50 variables, right? So if you want to see the structure of the data, if you want to see the structure of the data, so you can always see that. So you have these parameters. So sepal length, sepal width, petal length and petal width are numeric variable, whereas the last one is the character variable, that is the type of the data. So basically right now we are just finding out the principal component. So for that we have to sample our data. Let's sample our data into 2 partitions, that is the training data and the testing data. So replace is equals to true, and let's say the function, the training data, testing data, I am keeping it as 80 and 20. So train data will contain the first sample, okay, for all the columns, and test data will contain the second partition for all the columns, right? So let us partition the data, and we have the training data contains just a minute. So the train data is equals to, just a minute. Yeah. Okay, iris data SD is equals to 1, and yeah, here also iris data. So the second sample. So 2 data frames are created. So your training data contains 125 observations and test data contains 25 observations. So first of all, let us see the correlation. Okay, check the correlation between the variables. So let us check the correlation among the variables which are independent and which are correlated. So for that, let us create a graph, pairs.panel, that is train data. Now I am going to exclude the last column because it is the it does not matter, right, here, because since I am looking at just the correlation between the variables, I don't require the last column. So BG is equals to color. Let us color them so that we understand it properly. Red, and let's take the yellow color. and of course the blue color. Okay, not an issue. And here it will be train data. You have to check for the species, right? You have to, for the species, you have to find out which is the basically what is your how much relate they are related. Okay, so yeah, so we got this. Let us zoom and see the graph. You can see this graph. Let me explain you this. Now, these are the four columns related to the four variables, right? This is the sepal length. So, the correlation between the sepal length and the sepal width is minus 0.07, very less correlated. Then comes your petal length. Okay, so the correlationship between petal length and sepal length is 0.87, and sepal width and petal length is minus 0.39. Then with the petal width, the correlation of sepal length is 0.81. With sepal width, it is minus 0.33, and maximum is with petal length, that is 0.96. Okay, so here you can see there is the least correlation between sepal length and sepal width, that is the minimum among them, that is minus 0.07. Highly correlated between the independent gives variables will give rise to your multicollinearity problem, and if it is a multicollinear problem, then the predictions won't be correct. Okay, so what we are going to do here is that we have to remove this multicollinearity problem, that is between the petal length, petal width, it is highest, and then comes here between the petal length and the sepal length, right? And sepal width is very negatively correlated. This is what we could understand. So let us see, we can now apply the principal component analysis, but before that we have to scale the parameters. So let's say principal component as CPC is equals to P, the function is PRCOMP. Okay, principal component. So we are going to pass the training data, but excluding the last column. Okay, then center is equals to true, since we are going to normalize it, and scale is equals to true. So it will automatically scale all the parameters, right? So you can see here attributes of principal component. If you want to see here, you can see what are the attributes which will be computed. The standard deviation, rotation, center, scale. Okay, these are what are going to be seen. So if you want to see any one of the attribute, you can see, write down this PC center. So if you want to see the mean values, right, center values. So let's see, the center value is the 5.8344 sepal width and petal width. So if you want to find out the mean value of the train data of let's say sepal width, sepal length. Okay, let us see the mean value. See, same value you are getting. Okay, if you are, this is manually you computed the mean, and if you just put center, so you will get the mean value. So similarly, you can see, if you want to see the standard deviation. Okay, so you can write down similarly, you can compute for the standard deviation, right? And you can write print PC, principal component. Let's see the principal components. So here, how many principal components have been recognized? 4. PC1, PC2, PC3, PC4. So if you remember, they were orthogonal to each other. I hope you remember it, right? So if you go through that, okay, they have to be orthogonal to each other, each principal component. So if you remember, let us see here, you had, this is the first principal component we had seen, and this is the another one, second principal component. Dark blue line was the first one, dotted line was the second one. They are what? Orthogonal to each other. Orthogonal is 90 degree, right? These two principal components are orthogonal to each other. So here also you can see, yeah, we will plot it, wait, but we can see four principal components are there. The values of the principal component ranges between -1 to +1. Now you can see the principal component PC1 is having the highest value 0.5249. PC1 increases with increase in sepal length. Okay, when the sepal length decreases, the principal component also decreases. So PC1 will increase with increase in sepal length, petal length and width, because they all three were what? Highly correlated with each other. So the correlation was maximum between sepal length, petal length and petal width. But the correlation with the sepal width was the minimum, right? So it will decrease with the sepal width. So you can see with sepal width, the principal component is decreasing. Okay, but except for sepal width, other components, the principal component is increasing, right? So you can see for PC2 also it is given, for PC4, 3 and 4. So if you want to see a summarized view, so you can see the standard deviation in case of principal component 1 is 1.69, with PC2, PC3, PC4 variation, cumulative proportion, all the values are being given here, right? So PC1 captures the maximum variability. Why? Because the standard deviation is more, maximum. So it is going to capture the maximum variability. So if you remember here, so we want to capture the maximum variation in the data from here to here. PC1 is capturing. But in this case, PC2 is capturing the variance is very, very less. The fish example which I have explained, if you have missed that video, please go through that video. It will be very useful for you to understand the concept. So the fish example, this principal component 1 was capturing the maximum variability. Understood? So let us just see, and let us see the collinear relationship. Okay, PCX. Okay, that will show you that value. Gap is equals to 0, and let's say background is equals to C, and blue. So you can see here all the multicollinearity problem has been removed. See, all this has been, the collinearity is 0, right? So all of them solves the multicollinearity problem, right? Now, of course, you can do the predictions using your principal components. Instead of using the major features, you can use the principal components to solve your predictions. So let's say, instead of using the features, so predict, we are going to use the train data. So let's say target is equals to predict using C. Otherwise we used to write the features, right? But here we are going to use the principal components. So let's see the target, what predictions we are getting. These are the predictions, but of course this is difficult for us to understand. So let us say data frame, data.frame, then target, comma, train data fifth. We want just to see that is what is our prediction, right? See, here it is giving you the results. Otherwise it was very difficult for us to understand. No, here the fifth column was not added. So we have identified the fifth column here. Okay, so you can even give the test data also. So let's say test is equals to predict. You can predict it using the principal components. So test data. So test is equals to data dot frame test, comma, test data. Let's see, let us execute it. See, it has given all the values, answer, right? So now this is just, you have used this principal component for your training and testing, right? So if you want to use a predictive model, okay, you want to use a model, right, using the principal component for more than, we can apply this. Now, this is directly you have used the principal component. Now, let's say, for example, I am giving you what is the problem which will come here. See, what is the type of data here? These all are continuous data. So basically this problem is a regression problem. Now what type of regression is it? Is it a linear regression with single variable? No. Is it a linear regression with multiple? No, it is not at all a linear regression problem because it is a classification. So in regression, if you are performing classification, if you have binary output, if you remember, that is a logistic regression, right? If whether when your data is continuous but your output is classification. But here you have three classes, so you don't have a binary classification. Okay, it is more than two classes. So this type of regression problem is called as a multinomial logistic regression. Understood? So it is multinomial logistic regression where there are, it is a logistic regression only, but we have more than two classes. So for implementing your multinomial regression, you require this package library NNNet. Okay, let's say target species is equals to re-level, you will write, okay, is the level of factors because see, if you see the data here, you have like setosa is first. So let's see if I want to put setosa later on, like that. It's simple, just a function. I'm showing you how to use it. Okay, species and you can say reference is equals to let's say iris setosa. Okay. Now re-level will do what? I will show you. 1 minute. Yeah. Unordered factors. Okay. This is actually, let's say it is done. Okay. So that is why it is not only for unordered factors. So here they are ordered. So that is not a problem, right? Let's say we are going to call the multinomial regression. Okay. Let us do that. So calling, so if you want to call the, let's say the name of my model is my model multi-norm. Okay, where which is a type of logistic regression only having more than two classes. Okay, so you want to do it using PC1 plus PC2 plus PC3. I want to do only using the three principal components. Okay, data is equals to target. Or we can just simply give the test data, train data only. Yeah, we have to use the data target here only because target contains our target was used for this one, right? PC was passed, so it contains PC1. Otherwise, train data does not recognize PC1, PC2. Okay, let's see the summary of our model. So see, my model has been created, stopped after 100 iterations. So the model has been trained using 100 iterations, and you can see the summary here. So coefficients of PC1, PC2 for each of them, that is iris versicolor, iris virginica, they are given here. Understood? So this is how it is working. So you can even do the predictions, that how many predictions are correct or not. So that you have already done it. Okay, so I can stop my video here because anyway you know how to perform the predictions. So already you have seen how to perform the predictions. So you can use predict the function, and right now you can predict using your model for the target data, right? So you can even see, you can create a table. So table function you can use. You can see how your table looks like. So based on that, of course, you can, so since this is the table, you can say, so based on that, of course, you can compute your mat accuracy, diagonal of tab. See, with principal components, your it is coming very nice. Okay, tab. So you can see here 0.008. Okay, this is just the error. So if you want to see the accuracy, you can just see here 99.2% accuracy you are getting, right? Similarly, this you can do it for your test data also. So P1 is equals to predict my model you can use, and you can use the test data. You can create a table containing the values. Okay, P1 comma your test test data or test species. So you can see your table. Okay, and based on that you can compute your accuracy or the misclassification error. So the error rate has been reduced here. Okay, sorry, this is for table I'm doing. This is actually I want to do it for table 1. So I'm getting the same answer as last one. Okay, so 0.04. So if you want to know the accuracy, it is 96% accuracy you are getting using the model which you have created using the principal components instead of doing that. So basically what we could do is that we have tried it using the multinomial classification we have implemented. So instead of putting those variables like sepal length, sepal width for a multinomial classification, we have used using a principal component. So this principal components which we could find out first using the principal component function. So I hope you understood this video, and if you have not understood, you can write to me in the comment section, and of course you can go through my video on the theory of principal component analysis to understand in depth. Thank you, and please don't forget to like, share and subscribe to CSE Core Concepts.